Hello and welcome to this lecture. We've been looking at continuous random variables, in particular the probability density function for continuous random variables and how one can do calculations with it. One of the things we did for discrete random variables, if you remember, is after we looked at PMF and all that, we studied a lot of common distributions, particularly, you may remember Bernoulli, binomial, geometric, Poisson, things like that. So standard distributions that show up over and over again when you want to model something in practice. So like that, in the continuous case also, when you want to do modeling, there are a few common distributions that show up again and again and again. They're so common that we have to know them quite well, and we're going to do that in this lecture. We're going to see only three distributions. There are in fact so many of them and so many different types of applications, and as and when we meet other distributions I'll introduce them, but these three are really common. So let's start looking at it. Okay. The first one is the uniform distribution. We had the uniform discrete distribution, which is there is a finite discrete set and the random variable is uniform in that set. So that was a very simple distribution to describe. So in the continuous case also you can have a uniform distribution. Now you say that a random variable x is uniform square bracket a comma b. So now that is an indication that it is a continuous random variable and it's continuous between a and b. Okay, a random variable that's continuous between a and b and uniform between a and b, not just continuous and uniform in a and b, basically has a flat PDF in that range from a to b. The PDF is flat. Okay. Now from a to b, if the PDF has to be flat and it has to integrate to 1, the height of the PDF has to be 1 by b minus a, right. So that's the picture that you have here for the PDF. This would be a, this would be b, and the height here would be 1 by b minus a. Okay. So that's the description of the PDF of a random variable which is uniformly distributed from a to b. You can see why the uniform comes in. You take any interval between a and b, as long as the width of the interval is the same, the probability of the random variable falling in that interval is the same, right. So what is the, so if you look at this interval, for instance, probability of, so this is 0, so remember this is 0. Okay. So this area is the probability of a random variable falling in the interval. As long as the width of the interval is same, wherever you situate it, you will get the same area, isn't it? Wherever you keep it, as long as the width is the same, right? So if this is say some w, and if this is also w, probability of x here is w by b minus a. Probability of x here is also w by b minus a. So wherever you situate this window of with w, you're going to get the same probability. So that's the uniform distribution. But remember, this is a continuous random variable, So probability that x equal to any value is going to be 0. Okay, so that we don't model it like that. It's just any interval, as long as the width is the same, wherever you go, you will get the same probability. Okay. So what is this? This is probability. This is also probability of x falling in the interval. Okay. So the CDF is basically the integral of the PDF. You can see for less than a, the integral is all 0. From a onwards, it starts increasing. It will increase linearly, and at b, it will go to 1. So the formula is sort of like this: x minus a by b minus a, and it's 1 for x greater than or equal to b. So this is 0. This guy is 1. This is a, this is b, and you can see this formula would be x minus a by b minus a. Okay, it's easy enough to see. So that's the CDF, but PDF is very clear. It's flat, and it works out very nicely. Okay, so now if a and b are close together, the height will start increasing. Okay, 1 by b minus a will keep increasing as a and b come close together, and as a and b separate out, the height will fall down. 1 by b minus a falls down. Okay, so keep that in mind. Okay, so that's the uniform distribution. Okay, one can do computation of probability here. So here is a uniform distribution from minus 10 to 10. So fx of x, start with writing out the PDF, is 1 by 20. for minus 10 less than x less than 10 is 0 otherwise. Okay. This is the PDF, and any probability. So it's just you have to find the width of the interval and simply multiply it by 1 by 20, isn't it? So probability, let's just write down a few of these guys. Minus 3 less than or equal to x less than or equal to 2. It's just width is 5, right? So 5 by 20. Okay, 1 by 4 if you want. Probability, 5 less than mod x less than 7. Now once again, mod x means, this is the same as probability that 5 is less than x less than 7. X is between 5 and 7, or it's a disjoint union, so you can as well subtract it out. So you'll get 2 by 20 plus 2 by 20, that's 4 by 20. You can also calculate it in so many ways. So there's this 1 minus epsilon, 1 plus epsilon. All that matters is the width of 2 epsilon. So probability of x naught minus epsilon less than x naught plus epsilon is going to be 2 epsilon by 20. Okay, for any x naught. Okay, x naught inside let's say minus 9, something like that. Okay, so an epsilon small. Okay, so x naught is inside sufficiently. I'm just doing it so that x naught plus epsilon won't go outside of 10. Okay, so that's a problem. So as long as x naught plus epsilon is less than 10 and x naught minus epsilon is greater than minus 10, this would work. So you can take something like this. So this would be also working out. So that covers 1 minus epsilon, 1 plus epsilon being 2 epsilon by 20. So it doesn't matter what x naught is. This is independent of x naught, right? Wherever you situate x naught, you're going to get the same probability. So look at the next computation. Maybe this is a bit interesting. So it's probability that x is greater than 7 given probability that x is greater than 3. So this is just conditional probability. And what is conditioning? So x greater than 7 and x greater than 3, right? So this is the intersection divided by probability that x is greater than 3. Now what is probability that x is greater than 7 and x is greater than 3? It's just probability of x being greater than 7 by probability of x being greater than 3. So greater than 7 is 3 by 20, greater than 3 is 7 by 20, so that's just 3 by 7. Okay. So if you want to contrast, or if you want to say, for instance, probability that x is greater than 4, you're going to get so maybe I should do this. X is greater than 4 given x is greater than 0. Okay. So this is also like the 7, 3, right? So the 7 is 3 plus 4, isn't it? And 4 is 0 plus 4. So basically, x is greater than 3. What is the probability that you're going to be conditionally 4 away from 3? So likewise, x is greater than 0. What's the probability you're going to be 4 away from 0? So if you do the same calculation here, you'll get probability of x is greater than 4 by probability of x is greater than 0. This is going to be 6 by 20 by 10 by 20, 6 by 10, or 3 by 5. Okay. So different probabilities like this, you can think of conditioning and all this, and you can get it. So uniform is, I want to hopefully convince you, it's a very easy distribution to calculate probabilities for. There's no need for complicated integration, no need to remember any formulae. It's just the width times the height. Very easy calculation for the probability. Okay, so let's go to the exponential distribution. So this distribution is also very common, and here is the PDF and the CDF given for you. So this is a notation. X tilde is like x is distributed exponential with parameter lambda. Okay, so there's this parameter lambda. So in the uniform case, we had two parameters, right? A comma b, the starting point and ending point of the interval. In the exponential case, you have only one parameter lambda, and the PDF is lambda e power minus lambda x for x positive. Okay, so let's look at this plot once again. X positive, so this is 0, this is also starting at 0 like here. For x is equal to 0, you're going to get lambda here. This height is lambda, isn't it? So and then it falls. So this is just lambda e power minus lambda x. Okay, so is this a valid PDF? Okay, so it's non-negative. It's continuous, all right. Okay, so piecewise continuous, and then does it integrate to 1 is what you have to check. you can check that it will be valid. So if you integrate, you're going to get this integral will be e power minus lambda x, and you have to go from 0 to infinity, and that will work out as correctly 1. Okay, so this is a valid PDF. You can check that. Okay, but notice here a couple of things that are different between uniform and this. Uniform AB, it was the support was finite. Okay, it was only between A and B. Exponential, the support is an infinite length set, right, 0 to infinity. Okay, so it keeps on going. It does fall down quite rapidly, but it never hits 0, right. Fx of x never becomes 0 when x is positive. Okay, so it slowly keeps on decaying. It just goes down forever and ever, but it never becomes equal to 0. Support is very large, but it keeps falling quite rapidly. So it's much more likely to take values close to 0 than say close to 100 or something, right. So you can see why that is true. The PDF falls like that. Okay, so if you were to do the CDF, you have to integrate this guy. For x less than or equal to 0, you're going to get 0, right. So there's no area under the curve here. For x being greater than 0, you have to integrate the PDF from 0 to x naught. Okay, so the way to do this CDF, for instance, is fx of x naught is integral 0 to x naught lambda e power minus lambda x dx. So this is minus e power minus lambda x from 0 to x naught. So you will get 1 minus e power minus lambda x naught. So that's the formula here. So fx of x is 1 minus e power minus lambda x for x being greater than 0. Now does it eventually go to 1? If you see this this calculation, so you can see it will eventually go to 1. Okay, 1 minus e power minus lambda x. As x keeps on growing, if x becomes 100, 200, etc., e power minus lambda x will start falling down and down and down. Eventually it will become 1. So it's a valid CDF as you can expect. Okay, so this is called the exponential distribution. You can see why, because the exponent function plays a role. It's falling exponentially. Quite a few random variables in practice take this distribution. Okay, so it's a good model for many situations. Okay. Okay, so let's do a few probability computations here. It's very similar to before. So this x is exponential with parameter 2. So the PDF of x is 2 e power minus 2x for x greater than 0, 0 for x less than or equal to 0. So this is the PDF. And if you want to do probability of 5 less than x less than 7, it's going to be integral 5 to 7 2 e power minus 2x dx, and this integral is minus e power minus 2x. Okay, so between 5 and 7, so it's e power minus 2 times 5, which is 10, minus e power minus 2 times 14, which is 2 times 7, which is 14. Okay, so there's a minus sign. So e power minus 14 minus e power minus 10, there's a minus sign overall, so it gets flipped around. So you see, this is already very small, e power minus 10. So you remember e is roughly 2.7 something, right? So 2 power minus 10 is already like 1 by 1000. This 2 power minus 14 is already very, very small. So this whole thing is a small probability that x falls between 5 and 7. It decays quite rapidly. Let's look at these other things. So probability that 1 minus epsilon less than x less than 1 plus epsilon. You can do the same calculation. It's e power minus 2 1 minus epsilon minus e power minus 2 1 plus epsilon. Okay, maybe you can pull e power minus 2 common outside, and you will get e power 2 epsilon minus e power minus 2 epsilon. Okay, so this is the probability that you get, and the other one is 9 minus epsilon less than x less than 9 plus epsilon. So basically this question has the same width interval 2 epsilon, one located at one interval at 1 around 1 minus epsilon to 1 plus epsilon, the other one around 9. Okay, what's the probability that x takes a value close to 9? What's the probability that x takes a value close to 1? That's the kind of question we are asking. Okay, so this is turning out to be e power minus 2 times e power 2 epsilon minus e power minus 2 epsilon. Okay, so that's one value. If you go to 9, notice what happens. It's e power minus 2 9 minus epsilon minus e power minus 2 9 plus epsilon, and this is going to become e power minus 18 times e power 2 epsilon minus e power minus 2 epsilon. So notice look at this probability. This has gone much smaller than probability of 1 minus epsilon less than x less than 1 plus epsilon. So, the same width, notice how non-uniform it is, e power minus 18 is just really small. Okay. The same width of 2 epsilon around 1 has a much more higher probability of occurring than that same width around 2 epsilon. That is the PDF falling exponentially fast for you. Okay. So, let us look at this calculation here. There are two calculations, probability that x is greater than 4. Okay. This is going to be 1, this is 1 minus probability that x is less than or equal to 4, and we can even do it a bit differently. You can use the CDF here. So, it is 1 minus e power minus 8. So, you just get e power minus 8. Okay. So, it is easy to get this game. Now, look at this other one, probability that x is greater than 7 given x is greater than 3. This is going to be probability that x is greater than 7 by probability that x is greater than 3. It's just like this calculation, it will be e power minus 14 by e power minus 6, e power minus 8. So, notice this calculation here, probability that x is greater than 4 and probability that x is greater than 7 given x is greater than 3, they work out to be the same. In fact, you can show this in general, probability that x is greater than s plus t given x is greater than s is actually e power minus t. Okay. So, it's not very hard to see this. So, it is e power minus t and this in particular is independent of x, independent of s, independent of s. Okay. No matter where you keep your s, okay, s could be 1, s could be 100, s could be 1000, right. So, you're looking for the value of x, and if you are given that x is going to be greater than 100, probability that x is greater than 100 plus 1 given x is greater than 100 is the same as probability that x is greater than 1001 given x is greater than 1000. Okay. So, it does not matter where you are, that gap is what controls the conditional probability. The conditioning is important. If it is not conditional, then things change quite a bit. Okay. So, it is a nice property, it is an interesting property of, so this is unique to exponential distribution. No other distribution satisfies this property. Okay. So, it is a nice property of the exponential distribution to know. It is called memoryless property. Okay, this property is sort of like being memoryless, just whether x is greater than 100 or x is greater than 1000. Once you are given that, it is sort of the same from that point on. Okay. So, it is very common to use waiting time. So, for modeling waiting time, supposing you are waiting for a bus in a bus stop or you are waiting for something to happen, it is usually a random waiting time, right. So, that random waiting time is very commonly modeled as exponential, and you will see in many cases that is a good model, and no matter at what time you go to the bus stop, your waiting time is the same. So, given that you come so late, it does not matter what it is. So, that is sort of intuitive in practice, this memoryless property and how waiting times are controlled by that. Okay. So, it was just a small introduction to how this property comes in very handy when you model some real life situations. Okay. So, that is the exponential distribution. The next common distribution that we are going to see is this normal distribution. Okay. I mean, normal is also called Gaussian distribution. Okay. So, if there is one distribution that is most common in almost all models, it is the Gaussian distribution. So, it is not wrong to say when you are in doubt, if you do not know what the distribution of a random variable is, simply assume it is Gaussian or normal. Okay. It's so prevalent, it's so common, it occurs in so many different situations that one needs to have a lot of comfort in working with the normal distribution. Okay. There are two parameters. Remember, the exponential distribution had only one parameter lambda. In the normal distribution, you have two parameters. The first parameter is commonly denoted mu. The other parameter is sigma squared. Okay. So, sigma is, you can also think of the second parameter as sigma, but it is common to write it as sigma squared. Okay. So, this mu belongs to R. Sigma is positive real number. So mu maybe I should say is any real number can be positive, can be negative. Sigma on the other hand is a positive real number. Okay, so that's the constraint. So sigma squared is written that way. The PDF is slightly complicated looking PDF. It's got a sort of big structure, but let's see if we can unwrap it. So this 1 by sigma root 2 pi is a constant outside multiplying an exponential, so we can ignore that for now. And it's exp of minus x minus mu whole squared by 2 sigma squared. Okay. Now you can see that there is a negative sign here and you have x minus mu whole squared. Okay. So what's inside here is positive always. Okay. So x minus mu whole squared by 2 sigma squared is positive. So this minus will be negative. So this e power minus, as x becomes larger and larger and larger, much larger than mu, also it will go to 0. You can see here, so the picture goes like that. It goes to 0. Okay. And on the left hand side also, if x becomes much smaller, also this will become a very large positive quantity because you're squaring it, right? Even if x goes negative, because you're squaring, whatever the value of mu is, eventually it will go off all the way to very large value because of the squaring, and e power minus will drive it to 0. Okay. Where will it be maximum? You can see x equal to mu is where this will be maximum. Why is that? See, it's exp of minus some positive quantity, non-negative quantity. So what will be the way in which you can make this exp of minus very large? You have to make what is inside the exponent very small, isn't it? So this x minus mu whole squared by 2 sigma squared has to become very small. What's the smallest it can become? It can become 0, and that happens at mu. So this point is mu. Okay. And then this shape, how do you get the shape? This is this famous bell curve, as they call it. It's like a shape like a bell. Okay, and you can see how this bell shape will come. If you want, you can plot it using some numerical calculation. It's going to sort of fall like that, and you can, just think about it various ways why it should be like that, because it's a property of the exponential function. Okay, what is the height? I mean, if you look at the height here, that will be 1 by sigma root 2 pi. Okay. So in terms of why this is a valid PDF, it's non-negative, it's okay. Why does it integrate to 1? It's a complicated thing to show. Okay. So I will leave you to look it up. It's an exercise to check integral minus infinity to infinity fx of x dx equals 1. So another thing to remember is support of x is the entire real line. Okay. So a normal random variable can take any real value, okay, from minus infinity to infinity. When I say take, I mean take values in any interval on the real line. It could be from minus infinity to infinity. So support is the entire real line. There's no constraint, right? Remember, exponential, the support was only the positive thing. Uniform, its support is between a and b. Normal is entire real line. Okay, so there's no problem. It's sort of centered at 0. It's going to take values close to mu with higher probability, and as it goes both sides, it's going to decrease, right? So that's something you can see. All right. CDF is fx of x is integral minus infinity to x fx of u du, and there is no closed form expression here. Okay. So if you remember that for both the uniform and exponential, we had a very easy form for the CDF, x minus a by b minus a, and then 1 minus e power minus lambda x. So in this case, you will not have a closed form expression, because this e power minus x squared doesn't have a indefinite integral which is in closed form. So but the shape of the function, you can see it's sort of not too difficult to see. At mu, the value will be half. Eventually, it will go to 1. It will start at 0. So these are things you can show. Why should it be half at mu? Remember, this whole area, the entire area under the curve is 1, and then it's symmetric about mu, right? The area to the left of mu and the right of mu are the same. Okay, so each of them should be half. Okay, probability that x is less than mu equals half. So this is again an exercise you can show by symmetry. Probability that x is greater than mu equals half. You can put less than or equal to, greater than or equal to, doesn't matter. It's a continuous distribution, isn't it? So it doesn't matter. So this is both half, so that's a nice thing to see. So this mu is sort of like a central point. You can easily see that that is going to be true. Okay. So there is something called the standard normal. So if mu is 0 and sigma is 1, sigma square or sigma, because it's 1. So that's called a standard normal distribution. It's got a special name, normal 0, 1. Okay. So easily this is the most crucial distribution, and unfortunately it seems to have a complicated CDF, right? The CDF is not very easy, but the PDF is nice to draw. And today you can do numerical calculations for integration and find the probabilities that you want. Okay, so it's not too bad. This is the normal or Gaussian distribution. So let's see how to do probability calculations with this. There is a bit of a trick that one uses. This is the trick here. We will come back and justify this trick a little bit later on. So the CDF of normal distribution is does not have a closed form expression. I mentioned that. What you can do is this little trick of standardization. Right now I am going to just provide it to you without any proof, but this standardization is a very standard thing. We'll see a proof soon enough later on. Okay. So it turns out if x is normal with mean mu and variance sigma squared, then x minus mu by sigma is actually a standard normal. Okay. So it's normal with mean 0 and variance 1. Okay. So if maybe you can call this z. Z is a new random variable, isn't it? It's a function of x, and it is sort of centralized, standardized. You remember we talked about how to do this x minus mean by standard deviation to make this normal, make the mean and variance 1 in general. We saw it for other distributions. So this is sort of like that. We'll come back and see this in more detail later. But this is one trick that is used for tabulating the value of the CDF. CDF does not have a closed form expression. You have to look at tables, or you have to look at scientific computing software for giving you the value of the CDF. Okay, and for that this trick of converting to the normal distribution is used. Okay, so once you come to normal, that's the PDF and the CDF. It's 1 by root 2 pi e power minus z square by 2. Okay. So that's means sigma is 1 and mu is 0, right? So you get this. CDF has this integral expression which you can use in numerical computation and tabulate. Okay, so this is available in most places. If you get CDF for the normal distribution, you will get it. Okay. So to convert probabilities for a normal distribution, to compute probabilities for a normal distribution, you first convert the probability computation to the standardized case, and then you use normal tables. Okay. So we'll do this eventually. Let me not show you examples at this point. Maybe we'll see some examples soon enough. But this is the standard procedure. Okay. So in the exponential and uniform case, we could get closed form simple expressions for probability computations. In the normal random variable, you have to use tables, or you have to use a computer which has the CDF for the normal, at least the standard normal built. Okay. So this is the way you do probability computation. So here's an example. Soon enough, I was mentioning, I'll see an example. We'll do this. So this is normal with mean mu equals 2 and sigma squared equals 5. Okay. So z is equal to x minus 2 by square root of 5 is going to be normal 0, 1. Okay. So we'll assume fz is known, which is the CDF of z is known. Okay, that's the idea. And then we convert. So if you say x is less than 10, so that happens if instead of x, so this is, if z is x minus 2 by root 5, x is going to be root 5 z plus 2, isn't it? So instead of x, you put root 5 z plus 2. Root 5 z plus 2 is less than 5, which is the same as z being less than 3 by root 5. Okay. So now what is this? Probability of x less than 5 is equal to probability that z less than 3 by root 5, and that is simply f z of 3 by root 5. So we are going to assume this function is known, as in some table is given to you, or there is a computing software that's given to you, where if you plug in CDF of standard normal, it will give you the answer, right? So that's something that you can do. So this is probability of x is less than 5. The same thing with x is less than 10 or x is less than minus 5. I'm not going to do each of these cases. You can easily do all the x less than thing exactly the same way. If x is less than minus 10, then root 5z plus 2 is less than minus 10. That means z is less than minus 12 by root 5. It just changes what you put there, changes, and you get the same thing. Okay. What about x is greater than 5? Again, I mean, there's no real major confusion here. Greater than 5, that implies z is greater than 3 by root 5. And probability that x is greater than 5 is probability that z is greater than 3 by root 5. It's 1 minus fc of 3 by root 5. Okay, as simple as that. Okay, so this little bit of trickery in computing probabilities for a normal distribution, you have to pick up. It's a very simple skill, but the skill is very important. Okay, when somebody gives you a normal distribution with certain mu and certain sigma squared, you should be able to find probability for any event involving that random variable by converting to the standard normal and then looking up at tables or computing software for finding out what the CDF will be. Okay, so simple example. Okay, so here is another problem, and I think it's just been okay. So maybe I should do this. I'll do this a little bit in detail. So maybe 1 or 2 I'll do in detail, not too much. So mu is 3 and sigma is 1. So if you do this, z equals x minus 3 by 1 is going to be normal 0, 1. Okay, so normal, I've been writing out fully, isn't it? 0, 1. So if you want to look at 5 less than x less than 7, that's the same as, x is z plus 3, isn't it? So you substitute 5 less than z plus 3 less than 7, and that's the same as 2 less than z less than 4. Okay, so it's quite easy, isn't it? So probability that 5 is less than x less than 7 is going to be probability that 2 is less than z less than 4. And you know the CDF of z, isn't it? So it's fz of 2 minus fz of 4. Oh no, fz of 4 minus fz of 2, right? Sorry. Okay. So that's it. That's the answer for this problem, and every other range is also similar. I don't want to go into detail here. So let's look at the conditional calculation probability that x is greater than 7. Given x is greater than 3, again it's the same thing. I mean, I keep repeating the same calculation divided by probability that x is greater than 3, isn't it? Conditional probability works out like this. Now you convert x greater than 7, x is z plus 3, so that's the probability that z is greater than 4 divided by probability that z is greater than 0. Okay, probability that z is greater than 4 is going to be 1 minus probability that z is less than or equal to 4, and that is 1 minus fz of 4. And what is probability that z is greater than 0? Remember, 0 is the mean, the mu parameter for z, right? That's the center point. So probability that z is greater than 0 is actually a half. Okay, so this is 2 times 1 minus fz of 4. Okay, so you can do such calculations, whatever the probability may be involving standard normal, a normal distribution. You can do it in this fashion. Just that you assume, just like, this is not a strange thing to assume a particular function is known to you. You assume sin x is known, cos x is known, log x is known, e power x is known, right? I mean, nobody can actually give you the value immediately, but there is a computer which can give you the answer. So we assume that function is known to us. Similarly, this function fz we will assume is known to us. Okay, so it's a function that's known, CDF of the standard normal. Many packages and tables give you the value. Okay. So that's the normal distribution. So we've seen, so let me summarize what we saw. We saw 3 continuous distributions which are commonly occurring. It's used quite frequently in modeling: the uniform distribution, the exponential distribution, and the normal distribution. Okay, so we saw what the PDF is, we saw what the CDF is, and we saw how to do very basic simple calculations of any event involving random variables that are uniform, exponential, or normal. Okay, so that's a useful skill to pick up. Given the PDF and given the CDF, you should be able to find probability of any event involving the random variable. Okay, thank you very much and see you in the next lecture.